Okay, so today's lecture, we are going to talk about the second part of distributed training, part 2 of distributed training. This is the agenda for today. We are going to start with the hybrid and also the mixed parallelism and how to parallelize, auto-parallelize to choose from different parallelization methods, and also understand the bandwidth and also the latency bottlenecks of distributed training. Then we are going to talk about gradient compression to overcome the bandwidth problem, the bandwidth bottleneck of distributed training, including using gradient pruning. Can we allow sparse communication, and also how to apply deep gradient compression to reduce the communication bandwidth, followed by gradient quantization by using 1-bit SGD and also term grad to further quantize the gradients and reduce the communication bandwidth requirement, followed by delayed gradient update to overcome the latency bottleneck. So let's start with hybrid or mixed parallelism and also talk about how to auto-parallelize. And let's first review 3 kinds of parallelization opportunities for distributed training, starting with data parallelism. Okay, so we want to split the data. You have n copies of the model, and you have this is pretty high utilization but high memory cost, since you have to have the same copy of the entire model on each machines. But that can be potentially optimized by 0, 1, 2, 3 for fully sharded data parallelism. And here is some modern communication networking technologies from InfiniBand. It's just giving you an idea. EDR is 100 gigabit per second, HDR 200 gigabit, NDR 400 gigabit per second. So for the pipeline parallelism, we want to split the model by the layer. So each GPU is processing a certain kind of layers, and we pipeline them together, just like the pipeline stages in the computer architecture. After splitting the model by layer, we can have a single copy of the model across different GPUs that may have low utilization. Some slow layers have to wait. Some fast layers have to wait for the slow layer. Low memory cost, since each GPU handles only a subset of all the layers. Medium communication, unlike this one has low communication because the entire update happens locally on the machine. Finally, the tensor parallelism. So this is splitting across one single tensor. You can chop it into different parts and put each part on the GPU. So you split the model by the tensor. You have a single copy of the model. This can have high utilization, low memory cost, but high communication, since you have to, you are chopping, dividing the tensors, and you have to communicate with each other. We can also combine them, not just have 1 or 3, but combine them together. For example, in this case, in the outer side, this group of 2 GPUs and these 2 GPUs, we are using data parallelism. Okay? We are feeding different data to group 1 and also group 2. And even for the same group, we are using pipeline parallelism between these 2 GPUs, and also pipeline parallelism between these 2 GPUs. So these 4 GPUs, we assign them as 2 plus 2. Okay? Outer side is data parallelism, and inner side is pipeline parallelism. In this way, this is the 2D parallelism using this hybrid approach. Of course, there's C32. We can have other approaches. Like this one, we are having the pipeline parallelism in the outer dimension, and also tensor parallelism in the inner dimension. Okay? Tensor parallelism by chopping the tensors. This is the pipeline parallelism by dividing the layers. We can even do 3D parallelism, okay? Having this 3-dimensional orchestration. The same color denotes the GPUs on the same server. Okay? So here we are doing 0 data parallelism this way. We are doing model parallel in this way. Since the same color in the same GPU, we tend to have easier, faster communication sitting in the same node, so that we can divide the tensor among the GPUs that sits in the same node, since model parallelism has a huge amount of communication bandwidth requirement. And among GPUs, we do pipeline parallelism in this way. Immediately, the question is, the design space gets super big, right? How do we assign them? Okay, so when the model is too large to fit the GPU, we can split the model, okay, by using pipeline parallelism in this way, pipeline, part 1, part 2. But when the layer is too large to fit the GPU, we split the layer. We split the layer. Even for one layer, okay, we split it by GPU 1 and GPU 2. And split the layer using tensor parallelism. But this is a pretty large design space already. So how do we find the best parallel strategies? So there's a lot of research in this related domain. There's intra-operator parallelism, like tensor parallel. You want to chop within a tensor. An inter-operator parallelism, like for different layers, like pipeline parallelism. An automatic approach to assign different parallelization strategies. And I'm going to introduce ALPA from Berkeley that solve this problem, how to place these operations and layers when you have multiple machines and each machine has multiple GPUs. So that's actually a two-level assignment. So given a computational graph, there are many different approaches to parallelize them. Like we can have group 1, group 2, in 2 by 2 plus 2, or 1 plus 3, or 3 plus 1, or 2 by 2 plus 2. And even in each layer, we can chop it vertically, or we can chop it horizontally. This is an example where the interoperator parallelism, we decided to assign these two nodes in one GPU and these in another GPU. And intra-operator is horizontal, vertical, horizontal. So this is another example. These are two possible methods to divide it in the interoperator parallelism. So apparently, which one might be better in this case? Whenever you want a pipeline parallelism, you want to make sure what? The pipeline stage, the workload is roughly equal, right? So the fast one don't have to wait for the slow one, causing starvation. Remember from 644, right? So if you chop in this way, this is a pretty small layer. It will finish instantly. Then it's just sitting there idle while waiting for stage 1 to complete. Right? So this may not be a good solution, but this one might be more balanced. Stage 1, 2, and maybe this is a very fast one. So this may not be a good one as well. So we want to, rather than this kind of manually decide which one to group together, ALPA automatically find that. So this is about intra-operator parallelism. Okay, so even for a single matrix multiplication, A times B. So here the notation is that B is the weight, A is the activation, or A is the input. What kind of parallelization is this? Data parallel, because we have the same weight across different workers, and each worker is using different part of the input data. And this is type 1, type 2 for operator parallel. So we are dividing the weight tensor vertically or horizontally. Okay, so we can deploy different part of the matrix multiplication on different GPUs. And this is basically the design space for intra-operator parallelism. So what ALPA does is a unified compiler for distributed training to first figure out what's the best inter-operator path, and then the intra-operator path, and then orchestrate them to perform the runtime orchestration. It's optimized via automatic search, and not need to manually configure it, but it almost pretty much matches the specialized manually partitioned systems, and also outperform the manual baseline on in this case by a pretty large margin. So that is about the hybrid and also the mixed parallelization approaches and the way auto-parallelize that. And now let's switch gear to talk about what is the bandwidth and also the latency bottleneck in distributed training, and how do we handle them. So nowadays, like large language model, we have huge amount of data, okay, leading to pretty large model to provide enough model capacity. So that require distributed training so that we can have enough GPU memory and to fit those model and complete them, complete the training process relatively fast. Okay, so more data, you need more model, need more compute, more nodes leads to more communication. So communication is one of the key bottleneck about scaling. Okay, deep learning, why it's successful? Thanks to scaling. We want to scale up the training, scale up the model. So let's see the bottlenecks of distributed training in this slide. This is using the parameter server approach. We have gone through it in the last lecture. We first have a parameter server on the top. This is a parameter server. It's holding a single copy of the master copy of the neural network model. And may have multiple workers, a pool of workers. Okay, it need first get the copy of the model of the model's weights and train it on its local copy of the data, the local replica of the neural network model. So you get the local gradient. You have 4 copies of local gradient. We want to push and sum up in the parameter server. Okay, so this push and sum process requires synchronization, and that may become the bottleneck when we scale up the amount of worker nodes. So how much bandwidth is required so that the GPU doesn't have the starvation issue? So we just tested a bunch of models from Resident 18, Resident 50, Swing Transformer Tiny. It's a vision transformer. Remember, we learned that in the vision transformer class, swing base and also swing large. Number of parameters from 11 million parameters to almost 200 million parameters. And this is the iteration time on the 6000 GPU, batch size of 32 measured in milliseconds. It ranges from 20 to 500 milliseconds. To keep the GPU busy, how much bandwidth do we need? How do we calculate the bandwidth requirement? So in each iteration, assume we need to send the gradient in FP32. The dimension of the gradient, what's the dimension of the gradient? Is the same as the dimension of the weight. So in every, we can complete one iteration in 20 milliseconds. So every 20 milliseconds, we have to send 11 million parameters, or 11 million gradients as well. Okay? 11 million times 4 bytes, you get the number of bytes need to send for the gradient in 20 milliseconds. In that way, you can calculate the bandwidth required to do this work. And 1 byte is equal to 8 bit. This is G bit per second. It ranges from roughly 10 to 20 gigabit per second. And this is just the vision model. For large language model, this is getting much larger. And also training with more nodes, it requires more communication. For example, the all reduce. And also that will lead to longer latency. You see this figure is showing as we grow the number of GPUs, this is the speed up. Ideally, what do we want? You have 10 GPUs, you get 10 times faster. You get 100 GPUs, you get 100 times faster. But unfortunately, that's not the case. This is the ideal case, this is the real case. Okay? Ideal case with 250 GPUs, you get 250 times faster. But this is the measure result for Resident 152 is less. For AlexNet, it's even worse because AlexNet has 240 million parameters. ResNet has a lot more. ResNet 50 has 25 million parameters. You have to send more for AlexNet, so the scalability is worse. So our our motivation is how do we improve the scalability? So there are several bottlenecks, right? Compute, the memory bandwidth, and also the networking bandwidth. The lowest one determines in this water bottle, this bucket, the lowest bar determines how much water you can hold in this bucket, right? So if the networking or the memory bandwidth becomes the bottleneck, no matter how much compute you have, you are going to be bandwidth limited. Especially when we want to do distributed training not in the data center scenario, but in the Wi-Fi or cellular network, right? Since in the data center, you can easily get 100 gigabit per second by using InfiniBand, even 400 gigabit per second. Latency can be as low as 1 microsecond. But if you want to do federated learning, or if you want to learn through Wi-Fi or cellular network, the bandwidth is about 1 gigabit per second. It's keep improving, and the latency is in the order of magnitude of 100 milliseconds. So the high network latency will slow down the distributed training. So let's see. This is within the rack. This is the latency about 1 micro to 1 millisecond. We have full training speed. Same data center, within a data center with different racks. It's a little bit slower, but this is showing as we get wireless connection in the order of 100 milliseconds, slowdown is about 40%. If you are want to do distributed training across the world, like 500 milliseconds or 1 second latency, it will be like a lot slower compared with in a data center, right? So we are going to introduce compression techniques, just like model compression. Now we want to do gradient compression to overcome this bandwidth bottleneck. So including gradient pruning to enable sparse communication, and also achieved by deep gradient compression, which we are going to introduce several techniques to enable 1,000 times sparsity. So 1 in 1,000 gradient, we only keep 1 in 1,000 gradients. So again, the motivation is try to reduce the communication here, okay, when we want to push less gradient or parameters to the parameter server. So pruning is going to say that this is a dense tensor for the gradient. This is a sparse counterpart. Lots of them are zeros. Since they are zero, we don't need to send them out, potentially saving the communication bandwidth. Or we can quantize the gradient from 32-bit to lower precision so that I can save the communication bandwidth. So sparse communication. We not only have this sparse tensor, but we have a residual. Okay, so how do we select which one to keep? Actually, we are just using the top K approach. Okay, just sort the gradient tensor by the magnitude, and we keep the top K largest gradients. Very simple. And we may have a residual, which is the difference between the original dense gradient versus pruned sparse gradient. And how do we handle the residual, which is different from when we are pruning the neural network for inference? This is for training. There are many iterations. How do we deal with the residual? How can we improve the precision by taking some special treatment for the residual without having to send them out? We can actually accumulate it locally, right? I can have the copy. Our goal is just to reduce communication bandwidth, but it doesn't prevent me from updating being accumulated locally. Say if this gradient is pretty small, like 0.001, but after accumulated by like 10 times or 100 times, it might exceed the threshold, right? So we can accumulate them in the next iteration until it exceeds this threshold, it gets sent out. So we call it the error feedback. So keep the unpruned part as the error feedback. Actually, this method can improve the training speed. This is drop ratio from 90% to 99.9%. Images per second versus words per second can improve. This is experiment on a pretty old NVIDIA GPU. But what about larger networks apart from MNIST and NMT? Actually, we observed pretty significant accuracy degradation. This is not even on ImageNet. This is just on Cypher 10 by using a larger network rather than 101. So we observed about 1% degradation of the accuracy. So why performance degradation using the gradient dropping? Actually, we find that's due to a concept called momentum. And what is momentum? Recall what we have learned in the machine learning class 60336. When we are doing the update, momentum is a very widely used approach to overcome the local minima or the oscillation process, trying to stabilize the training trajectory. So you have a gradient, okay, and this is the previous step, the direction of the previous step. You discounted by a number that's smaller than 1. We call it the M, momentum. This is your previous direction. This is your new direction. So if without any momentum, what is your direction? You are going to go this way. But with momentum, you are going to combine the previous direction discounted with the current direction. So you are going to go this way. This is one iteration. Another iteration, this is the momentum from the previous iteration. This is the new gradient. So this is the new direction. The momentum is trying to smooth or stabilize this training process by taking the discounted factor of the previous direction. And we call this velocity. Okay? Velocity is a combination of the current gradient with the previous velocity, the previous direction. And when we are doing the update, when we are updating the weight, we are updating this velocity rather than updating the gradient itself. So the velocity is the previous velocity discounted by momentum plus the current gradient. So let's see what is going to go wrong if we use optimization without momentum correction, but doing gradient compression. So let's review it first. This is momentum. We do the update. Another gradient. We do the update. So if we are doing the pruning, okay, we are previously talking about accumulating the gradient, okay, in order to give it a chance when the accumulated gradient is larger than the threshold, it's going to be sent out. But is it correct that we accumulate the gradient rather than accumulate the velocity? Let's see it from the animation here. So if we don't do any momentum correction to apply deep gradient compression to prune those gradients and accumulate the gradients locally, if it is small, what will happen? So this is the vanilla momentum SGD, is momentum SGD with local accumulation. With local accumulation, we want to accumulate the gradients in the local buffer. So this is the gradient T, this is gradient T plus 1, similar to gradient T or gradient T plus 1. If we directly accumulate the gradient, what will happen? The sum, the accumulated gradient will be this red arrow. And if we add the accumulated gradient with the momentum, this is the direction that I'm going to take. By adding the accumulated gradient, this is the accumulated gradient, this is the momentum, and this is the new velocity. And actually, the optimization trajectories that doesn't match. One is going this way, the other is going this way, the sum of this one and this one. So the optimization results actually shifted, doesn't match. So that's create a big issue. Can we solve this problem? Are we accumulating the wrong stuff? What should we accumulate instead? Okay, here we are adding the velocity. Okay, so we should accumulate the velocity, not the gradient. So this is the velocity, okay, which is the sum of the momentum of the previous step and also the gradient. This is the velocity for the next step. So we should accumulate the velocity in this way so that it's equal to the previous two approaches, two steps. Okay? So accumulate the velocity through different iterations rather than accumulate the gradient. In that way, we call it momentum correction. So that when we prune those gradients, we shouldn't just accumulate the gradient, but just accumulate the velocity. So the optimization status now matches the vanilla momentum SGD on the left. So let's put them together to review this magic approach. So this is vanilla momentum SGD. The update is equal to the previous step plus the current gradient. And we just do a step, multiply by the learning rate, subtracted from the previous weight. This is without momentum correction. We are directly accumulating those small gradients which didn't exceed the threshold, and as a result, it didn't get sent out, accumulated locally, go in the wrong direction. But if we accumulate the velocity rather than accumulate the gradient locally, we can match the trajectory during multiple steps of SGD. Another important technique in deep gradient compression is using warm-up training. So in the early stages of training, the network is actually changing pretty fast. So the local gradient accumulation and stale gradient will aggregate the problem. So during initial training, it can be very steep. To alleviate that, we want to, of course, warm up the learning rate gradually rather than directly have a pretty big learning rate. We also want to warm up the sparsity rather than directly go to pretty high sparsity. We want to start with low sparsity and gradually enlarge the sparsity to avoid a sudden change in the sparsity. Exponentially increasing the sparsity in the first couple of epochs helps the optimizer to adapt to larger sparsity, and that's how we get to like 99.9 sparsity in the end. This is pretty amazing. This is the top line accuracy of ResNet 101 on Cypher 10 LSTM on AN4 without using the naive gradient pruning. They don't converge. Okay, similar for this one. This number of GPUs is 8 and 4 with local gradient accumulation. Okay, when the gradient is small, didn't get sent out, but we can accumulate them locally. Remember that feedback. The loss is about 1.5%. But if we add this momentum correction, the gap is only 0.3%. And also when we do a local gradient accumulation plus warm up, okay, it's about 1% gap. But if we put them together, combining the local gradient accumulation with momentum correction with warm up training, by putting them all together, we call it deep gradient compression, we can match the accuracy. Despite we are having 99.9% sparsity, meaning that among 1,000 gradients, we keep only one. We send out only one gradient value. Similarly for the other data set. And this is on Cypher 10, using 99.9% gradient sparsity, we can match the training curve very well. And this is on another data set. This is on ImageNet data set. The compression ratio for AlexNet is about 500, 600 times. This is for VGG, it's about 200, 300 times. Well, the accuracy is fully preserved, both the top 1 and top 5. And the gradient size, previously you have to send more than 200 megabytes of gradient. Now it's about 0.39 megabytes. So this is another task. We just want to verify it on as many tasks as possible. This is for language modeling. We can reduce the bandwidth by 462 times. You can see the learning curve matches pretty well. And this is for speech recognition. We can reduce the bandwidth by about 600 times, reducing from 400 megabytes to less than 1 megabyte. But what is the potential problem when we are doing the all-reduce process for sparse gradients? So remember, we have multiple GPUs, right? We want to communicate such that everyone has every other's copy of the gradient. Like we have 4 GPUs in this case, and in a ring, they have different sparsity pattern. Okay, 1 stands for there is a gradient. 0 means there's no gradient over there. When we are doing the all-reduce, for example, the ring all-reduce process, 0 give it to 1, 1 give it to 2, 2 give it to 3, 3 give it to 0. After one iteration, node 1 has both the information from itself and also the information from node 0. So in this case, node 1, the sparsity pattern will be this plus this, okay, from 0 and also 1. But what happened here? It's getting denser. Okay, previously it was pretty sparse. Now it's getting denser because it's taking the information from its neighbor. And the neighbor's sparsity pattern is complementary, not the same. If they also have the same sparsity pattern, say everyone is using this sparsity pattern after they communicated with each other and add them up, they still have the same sparsity pattern. But now the sparsity is destroyed. The more steps you go, the denser you will get. Let's see another example, node 2. What information does node 2 get? Node 2 get information from node 1. Okay, node 2, this is its original, this is node 1. And the first row is exactly complementing each other. So you get a denser gradient tensor. So in the next round of update, you have to communicate a lot of non-zero elements compared with the first iteration. Are there ways to alleviate this problem? So remember, we can enforce the same sparsity pattern so that you can do the communication without hurting the sparsity ratio, or use coarse-grained sparsity. Some paper talking about that. Given we have a huge opportunity to make it sparse, like 99.9%, this method will hurt the sparsity ratio a little bit, but enable us to have the same sparsity ratio across iterations. And possibly we can also prune in the middle of this ring or reduce process. Like after the first iteration, we prune it again to prevent, for example, we can prune this again to prevent it from getting denser. This remains to be seen. And another approach to overcome this potential issue is not using sparsity, but using low rank. By using low rank to address this irregular sparse pattern in gradient compression, okay, to prevent the gradients from getting denser across different iterations. And instead of using the fine-grained pruning, we can adapt the low-rank factorization. Okay, so this is like pruning approach, dense becomes sparse. This is the low-rank approach, dense matrix becomes a low-rank matrix, the product of two low-rank matrices. The low-rank matrix dimensions are the same across different servers, so they just need to communicate 8 elements in this way rather than 16 elements. No matter how many iterations they communicate, it's still 8. rather than this one might get denser. So this is the speed evaluation. This is SGD sigma rank 2, low rank approach. This is also the low rank approach. Scales pretty well. Well, this is the comparison, comparing the gradient pruning, gradient quantization, and this low rank approach, showing that low rank is actually pretty effective approach. So let's compare different gradient pruning methods. So gradient sparsification, we can first do this local gradient accumulation to give those small gradients get a chance to get accumulated, get large enough so that it can get sent out. But this has low sparsity ratio. But in order to achieve high sparsity ratio, we talk about deep gradient compression technique, which basically introduced this momentum correction. We should accumulate the velocity rather than the gradient. And also gradient clipping is also crucial. Warm-up training is also crucial. We can achieve pretty high sparsity ratio while maintaining the accuracy. And to solve this getting denser problem, we introduce this low rank approach instead of fine-grained pruning approach. So let's take a break before we jump into the next technique, which is gradient quantization. Okay, welcome back. Since we already passed the midterm, we want to make sure we collect your feedback. So the TA has already posted the feedback on the website. We appreciate your thoughts. It'll be anonymous. Just tell us what you like, what you don't like. Is it too fast? Is it too slow? Homework too easy or too hard? And we always hope to make the lecture better from time to time. All right, now let's switch gear to talk about gradient quantization using 1-bit SGD and also using the term grad. Can we use just 1 bit to quantize the gradients? Actually, it's possible. So given a 32-bit gradient, we can quantize that to 1 bit, and we have a delta. We have a delta, 32-bit delta. We actually can apply a column-wise scaling factor. So this is the original gradient. Okay? So we can compare with the threshold 0. If it's larger than 0, then it's positive. If it is smaller than 0, then it's negative. So it's binarized in this way. So we can add another scaling factor for each column, mu1, mu2, mu3, mu4. They can be 32-bit, they can be full precision, but the overhead is amortized across this entire matrix. So the overhead is much smaller. So we can use this to send it out. We can send out this binary mask together with the ON, the scaling factor, which is n rather than n squared. And similar to gradient accumulation, we can accumulate the quantization error locally on the node itself until next time it gets sent out. There's also a method using the threshold quantization. So we have to manually specify a threshold, a tau. If it's greater than tau, it's green. Smaller than tau, it's yellow. And otherwise, something in the middle is 0. Okay, so we can have this approach, use a tau to ternarize the gradient matrix. And also there's an approach called the term grad. The key idea is that we can quantize the gradient divided by the max of this gradient to 0, +1, and -1 with probability, with a probability. Okay, it's G divided by the max of this tensor. Why do we need that probability? Because we want to ensure the expectation of the G is the same before and after this quantization process. For example, if a max is 1.0, if the gradient is 0.9, we have 90% of probability is going to be quantized to 1. And if it is the max value is 1, but the value is minus 0.8, you have 80% of probability is going to be quantized to minus 1. So you want to keep the expectation the same. That's the key idea in this approach. And there's no quantization error accumulation, and it's quantized on the fly. So this is ternary quantization. You can send out 2 bits to reduce the communication bandwidth. But limitation here is you have upper bound about the saving you can have. From 32-bit to 1 bit, you can at most save 32 times for the gradient. But it's very regular. There's no irregularity issue. There's no denser and denser issue, unlike pruning. Okay, so we finished a big part about gradient compression to solve the bandwidth problem. For the remaining problem is the latency problem. Okay, overcome the network latency by delayed gradient update. What is the bandwidth versus latency? Just recap the concept of bandwidth versus latency. Okay, so bandwidth is easy to improve. You can always expand your bandwidth by, for example, buying more expensive or higher end hardware. Okay, you can upgrade your Ethernet with fiber, or even with Mellanox InfiniBand. Nowadays, you can get 400 gigabit or 800 gigabit per second. So this is a lot more faster than Ethernet. So you can do the hardware upgrade. You can also apply gradient compression to reduce the workload to communicate by using pruning techniques or gradient quantization techniques. So you can conquer the bandwidth problem relatively easily by either compressing the workload or upgrading the hardware. But latency is hard to improve because you have the physical limit at the speed of light. Traveling from Shanghai to Boston at the speed of light takes 162 milliseconds. That cannot never be broken. And also the signal congestion, okay, a lot of signal contention. So improving the bandwidth is easier, but latency is much harder. And let's see, how does the long network latency hurt the scalability and the speed? So this is vanilla distributed synchronous SGD. So the green part is the computation, the yellow part is the communication. As we increase the latency, you have a longer yellow part. So the local update and the communication are performed sequentially. You have to do the compute, communicate, and then compute. You cannot start the second iteration of compute until the first iteration's communication has finished. So the worker has to wait the transmission to finish before it starts the next step. This is similar to, if you're using analogy of homework, this is like we release the homework 1, finish the homework 1, and then we release the homework 2, and then you finish homework 2. We cannot release homework 3 unless you finish homework 2. But an amazing invention is the late day. We can use late day to handle the homework. What about, can we use the late day for distributed training to allow stale gradient? Okay, so we can overlap the communication with computation. So when you are doing lab 2, we already released the lab 3. They are overlapped. Let's see what exactly does that mean. So this is without any delay. All the local machines are blocked. They have to wait for the synchronization to finish. Okay, there's a long time between during this send and receive of the parameters. But if we can allow the delayed gradient averaging to use stale gradient, we can start the second iteration before we actually receive. Previously, we have to receive to the accumulate to the gradient communication, have that finished before we can start step 2. Now we can start step 2, iteration 2, without being blocked by this communication. We can start step 2, step 3, step 4, until we finally received the gradient from other workers. So now I apply this gradient update since I have received it from other workers. But now what I applied here is something that is 3 time step ago. It's a stale gradient. So the worker keep performing local updates while parameters are in transmission, and then I can apply this stale gradient. And similarly, at step 5, we are applying the gradient that is actually performed, calculated during step 2. So how do we implement that by code? So for iterations, we calculate the gradient, we send the gradient, the ID is the current iteration, and then we maintain this list of our iterations. We use the current gradient to populate this array, and then we receive the gradient that was actually sent the iterations before. So we are receiving an old gradient since the gradient communication takes time. When we are doing the update, we first apply the current steps gradient G, and then we kick out our own gradient that was D steps ago. We put it in an array to remember, keep a buffer of several steps. In this example, we have to keep a buffer of step 1, 2, 3 until we get 4. So we need to maintain a buffer, keeping track of our local gradient. So here we are kicking out our local gradient D steps ago. We finally received the average G from other workers coming from D steps ago, and we add it up. So kick out our old gradient and take in the new gradient, the outdated gradient sent from other workers. So this is like on the right-hand side, rather than we have to do the communication and synchronization step by step, we can now delay the step. In this case, we delayed by 1 step. As long as the communication can finish before here, it doesn't hurt our total throughput. So we are pushing back the synchronization barrier by allowing stale gradient. So delaying the receiving timing of the ith gradient to a later iteration, D steps later. So compared with original approach, as you increase the communication latency, it slows the training. The training 4 steps, this one is longer than this one. But if we can delay the synchronization barrier by one step, as long as the communication is shorter than the computation here, we can allow the same time of completing these 4 steps of gradient calculation compared with the first one. So this is showing the ResNet 18 with the correction versus without the gradient correction, which is basically this term. You kick out your own term, your own gradient that was D steps ago, and also you want to take in the average gradient you received from other workers that was sent D times ago, D steps ago. Finally, you received it now. So we call it this, the gradient correction term. So you cannot just receive from others, you also want to kick out your own stale gradient. We can see the accuracy is getting much better than without such gradient correction term, which is right here. And on the right-hand side is the illustration of delaying it by 3 or 4 steps. Like at the 4th iteration, the averaged gradient from the first iteration actually arrives. And when we are applying the optimizer, we need to calculate the Wij. So this is a naive approach without any correction term. We're just using our current gradient from myself, from my current worker, and this is the averaged gradient from other workers, but D steps ago. Basically, this is corresponding to without correction. We found it doesn't work but what we need to do is wij minus a term. Okay, we have to subtract the gradient sent by myself that was these steps ago, and then take the gradient that is averaged from all other workers from these steps ago. So this is the accuracy evaluation on Cypher, ImageNet, and also language modeling tasks. So the speed up ranges from 2 to 4 times, which is pretty good. We tested IID and also non-IID scenario, and we compare with the fed average approach. The delayed gradient averaging approach can consistently have better speed up and with even better accuracy compared with without it. Like here and here, the accuracy improvement is actually quite significant here and here. So that enables us to do distributed training with low cost networking and with poor edge devices. So this is a real world benchmark on a tower of Raspberry Pi. So here we have 1, 2, 3, 4. We have 8 Raspberry Pis. We stack them together. The communication, certainly we don't have those high speed networking, but we can still perform on-device distributed training or federated learning. We tested scalability from 1 node to 8 node. And here we can observe the speed on vision tasks and also on the language task. So this is, we compared several approaches, the fed average using different parameters, and also the delayed gradient averaging. And with 8 node, we can actually get 7.5x speed up, or 7x speed up for vision, or 7.5 for language. It's empirical. It's a trade-off between the networking latency and accuracy. So if you know your iteration time, for example, here, you know this is your iteration time. You can calculate it by running a job, and then that can determine the max number, the minimum number of iterations you need to have. For example, if you delay by 1 iteration, you can tolerate this latency. If you delay it by 2 iterations, you can delay 2 iterations latency. So given your network bandwidth, you know your networking latency, and also you know the compute latency for each iteration. So the number of delayed steps would be dividing the network latency by this compute latency for 1 iteration. Then you get how many iterations you need to delay. All right. So this is summary for today's lecture. We talk about first mixed parallelism, hybrid and mixed parallelism, and also how to automate this process for data parallelization, model parallelization, and also the pipeline parallelization. Then we understand the bandwidth and the latency bottleneck in distributed training with 2 approaches to conquer that issue, using gradient compression to overcome the bandwidth bottleneck by using gradient pruning, sparse communication, deep gradient compression, momentum correction to enable gradient pruning, and also gradient quantization using 1 bit or 2 bits. To conquer the networking latency bottleneck, we discussed about the delayed gradient update. So with that, I would like to conclude today's lecture and take a question. Momentum correction. Yeah, that's a good idea. I think we can explore that. Atom, they have 2 states rather than have 1 state. You probably need to take care of both states, optimization states. So as promised, I'm going to do a lab tour to show you how these large models are trained. So just follow me, and Han will go to the basement to show you our distributed training infrastructure.